Hi everyone, my name is Christian Jacob and we'll use the next 15 minutes to talk about methods we use and why we do the things the way we do. So first of all, as you may now know, our main goal is to give producers and agronomists reliable data on with which they can work to minimize pesticide spray or in certain instances justify their use whenever necessary. In order to do that, we provide information on weather data and the risk of disease in those weather conditions. And perhaps most importantly, we provide information on the concentration of spores present for targeted disease that are released in air. So first of all, what is a spore? Um, so a spore is like the pollen to a plant. In fact, molds have many features comparable to a plant or a tree. They have mycelium, reminiscent of the roots of a plant. They have a stalk, branching patterns, fruiting structures that hold cells or spores in that case. Uh, and those spores are released in the air and responsible for the dissemination of the fungus. And that is where we can intervene by capturing those microscopic seeds before they actually cause damage. This is giving you a window of opportunity to act and prevent the disease to take foothold or to progress. So when talking about disease prevention programs, to be usable, a prevention method must have specific uh, characteristics. It must be simple and reliable, assess risk throughout the season. It must be easily usable in rural settings and offer a quick turnout. And these desirable aspects were kept in mind along the development process of our program. Um, so when talking about spore collection strategy, we knew early on that we wanted to ally spore trapping and weather data analysis to have a complete and precise picture of what is the actual disease pressure in a specific field. So a number of options are available for spore trapping. The spore trapping devices are divided in different categories depending on how they operate. And there's a number of trapping designs in each category, each with their own specific pros and cons. Here I just represented a few that are perhaps the most used or most recognizable. So first of all, spore collectors can be described as passive or volumetric. Um, Passive traps are defined by the fact that they rely on either inertia, gravity, or winds to operate, mainly winds. Uh, they have the big advantage of being very inexpensive. They also offer continuous sampling without assistance. And the main drawback is that it's extremely variable. Its efficiency is extremely variable because of the fact that it relies heavily on winds. Then volumetric sampling spore trap, for their part, use mechanical pump to set to a precise flow rate, and thus we know precisely the volume sampled. This means that these sampling tools have known air volume and measurable efficiency. They are also less dependent on weather conditions. They allow for continuous or targeted sampling. And perhaps the main drawback is their propensity to overload, and we'll cover that in a few minutes. Then traps can be stationary or mobile, meaning that they either use equipment that remains on the ground or equipment perched on a fixed pole, or in the other case, equipment that can be carried in the field and placed wherever need be. So for example, if you have a field such as the one highlighted here with dominant winds blowing southeast, you would likely place your stationary and mobile spore traps on the southeast edge of the field to sample in order to sample air that passes over the field, giving you a chance to find spores of interest that comes from afar or from your field. Um, but if we tweak the wind direction just 45 degrees, it gives a much different result. The mobile spore trap will be positioned at the optimal spot, but the stationary sampler misses most of what passed over the field. So although it's cheaper, more traps and more analysis are necessary to achieve the same work. So to us, the best strategy seemed to imply using a mobile and a volumetric sampler. I won't go into more details on why these devices and not others in the category because of the time constraints, but let's just say that we went for a simple and effective. Next up, when thinking about spore sampling and most importantly about real life situation usage of data derived from spore sampling, turnaround time is absolutely critical and is often overlooked. The time frame between spore deposition and disease can be quite small, as you can see here for late blight. It can be as soon as 4 days after spore deposition. So agronomists and growers must receive their reports within this time frame. So a useful sampling calendar that has the grower's interest in mind must involve harvesting samplers or going into the field to take samples every 2 to 3 days at most. Uh, this gives us 1, 2, or perhaps 3 chances to detect the disease before it becomes visible by traditional scouting methods, or before it's too late to do anything. Then we did touch on the propensity to overload with the samplers we decided to use. This actually forced us to think a little bit differently and allowed us to be even more efficient with disease detection. We went back and studied the dynamic of spore release and spore viability, mainly for late blight, but for other diseases as well. And after looking for ways to mitigate this limitation of our sampler, we realized that, of course, it's actually better to massively sample within the window of time where the spores are released in masses and are also viable than sampling throughout the whole day. For example, this high spore concentration release for Phytophthora infestans causing late blight usually occurs in the morning after the dew dries up. Again, for the analysis in the lab, we made sure to keep things as simple as possible. While I'm a big fan of biochemical methods and PCR protocols, and I have personally used this technology in just about every research project that I've ever done, and they're great tools. But to make sure that our process did not rely on cumbersome and expensive equipment and sensitive regions, we went with identification by microscopy with a cleverly designed spore trap that simply encloses a microscope slide. So it only requires one person, his or her microscope, and about 10 minutes of their time. So again, I don't want to go too deep into details, but we gather as much information as possible through microscopic observation and by comparing key traits with known species from the scientific literature, we can assess if the spore of interest are present in the sample or not. At first glance, this method can seem very challenging given thousands of species of fungus that releases spore in the air, but luckily for us, potato pathogens are, for the most part, quite easy to identify by those means. Now the weather aspect. Uh, Spore analysis by itself is an incomplete story, just as weather assessment alone is also an incomplete story. Much better than nothing, but still incomplete. So to have this disease, of course, you need the presence of a host, the pathogen agent, as well as favorable weather conditions. So all those traits are equally important. There are two main ways of approaching weather data, forecasting and simply condition assessment. So for forecasting, in reality, forecasting of disease and spore trapping are, for the most part, two measurements of the same phenomenon. Models estimate the likelihood of occurrence of each of the many steps leading to spore germination and plant infection. So those models are often used on their own without spore trapping. Because we are physically there 3 times a week to trap spores, we shortcut all those variables and estimations that are quite complex to manage to verify if the spores are there, and then we simply assess if the weather conditions present on that given day and in previous days were adequate for disease. Then one last point that I wanted to touch is the establishment of thresholds. Uh, while it's very tempting to use specific breakpoints over which an action would be required, there are still way too many variables for any threshold to be usable. Spore density, although a crucial data point, does not correlate with disease severity. It does correlate with disease presence in the field or in the area around the field, but not necessarily with severity of the disease. So any given number of spore detected is a consequence of many variables: canopy density, wind speeds, host susceptibility, soil composition, air humidity. Um, so of course, for some diseases like late blight, one spore could be considered one too many and trigger an action. But for early blight, presence or absence and trends over multiple data points are probably more what should drive your actions rather than one specific number. Um, Then, although there are many more subjects to cover and a lot of information to discuss around those points that we touched today, I hope that this quick overview got you all thinking perhaps a little differently about spore trapping and all the variables that come into play. Please do not hesitate to send in your questions via email if needed, and I thank you all for your time.